WIMI Hologram Academy, EOG-based human-computer interaction technology in virtual reality. Virtual reality technology, as an advanced computer simulation technology, has been widely used in many fields. In the medical and rehabilitation fields, for disabled patients with physical injuries, virtual reality-based rehabilitation training can provide them with interesting and comprehensive training, accurate sensory feedback, and a safe training environment, according to the patient's psychological state and condition. Virtual reality technology can select corresponding rehabilitation training scenarios and tasks, stimulate and maintain the patient's initiative in rehabilitation training with various forms of feedback, and improve the rehabilitation effect. Immersion, interactivity, and conceptualization are the three basic features of virtual reality systems. Traditional virtual reality interaction methods mainly include VR handles, data gloves, motion capture, etc. With the continuous development of information technology, some new methods of human-computer interaction technology for virtual reality have emerged. For example, interaction based on neuron electric signals such as EEG and EMG. These emerging human-computer interaction technologies have greatly enhanced the immersive experience of virtual reality. Scientists from WIMI Hologram Academy of WIMI Hologram Cloud Inc. discussed in detail a new type of virtual reality interaction technology, the electro-oculography-based interaction. The EOG signal-based virtual reality interaction system mainly includes three parts, which are the signal acquisition part, the EOG signal processing part, and the virtual reality scene part. When the system works, the user receives the excitation signal from the virtual reality scene in real time, and the user makes corresponding eye movements according to the excitation signal. The signal acquisition equipment collects the user's EOG signal in real time, and then converts it into control commands for the virtual reality scene through a series of signal processing, so that the virtual reality scene executes the corresponding commands and gives feedback to the user in a visual way. The EEG signal is caused by the difference in electrical potential between the cornea and the retina, and can be used to reflect eye movements, with amplitudes generally ranging from 0.4 to 10 MV. Compared to EEG signals, the acquisition of EEG signals is relatively simple and convenient, usually requiring only a few electrodes. Generally speaking, 6 electrodes can be used to acquire EEG signals. Electrodes A and D are located above and below the eye and are used to collect the vertical EEG signals, which are mainly generated by up and down movements of the eye or blinking, while electrodes B and C are located on the left and right side of the eye and are used to collect the horizontal EEG signals, which are mainly generated by left and right movements of the eye. The EOG signal usually has higher amplitude and more stable waveform shape compared with EEG signal, so it is easier to detect. The EEG signal processing mainly includes several major steps, such as signal pre-processing, feature extraction, waveform detection, and classification recognition. There are many methods to pre-process the original EEG signal, including signal amplification, baseline calibration, artifact removal, downsampling, and other methods. The frequency band in which the EEG signal is located is low, and the original EEG signal is generally mixed with other bioelectric signals and external power frequency noise interference signals. So in the pre-processing link, generally through low-pass filtering, wavelet transform, and other methods to attenuate or eliminate the baseline drift and high-frequency noise brought about by the interference. The basic principle of waveform detection is to determine whether the subject performed a valid single blink by the amplitude and signal duration of the feature vector f. In other words, the differential EEG waveform obtained after the above pre-processing. Experiments indicated that there was a very distinct peak-valley characteristic in the differential EEG signal waveform, and the valley appeared after the peak. To detect the extracted feature vector f after each excitation signal, We first need to find the locations of the peaks and valleys in F. The largest value in the extreme value of the feature vector F is considered as the peak, and the time point corresponding to the peak is set as T peak. The smallest value in the extreme value is considered as the valley, and the time point corresponding to the valley is set as T valley. Then, for the obtained feature vectors F corresponding to different excitation signals, the interval time T interval between the wave peak and the wave trough and the accumulated energy E in each feature vector are calculated separately. And finally, the existence of blinking action is judged by EOG. Before feature extraction, a single EOG data segment is generally extracted, and the length of the data segment is designed according to the actual situation. And the feature vector is also generally extracted for a single cycle of the EOG signal. It should be noted that the extracted feature vectors should effectively represent the characteristics of the EOG signal, have good differentiation and independence, and be easy to compute. The methods of EOG signal feature extraction include shape feature extraction method based on signal waveform, wavelet transform method, etc. Currently, the most common method used to classify the features of EOG signals is the threshold method. In addition, methods such as support vector machines, BP neural networks, and linear discriminant analysis can also be applied to the classification of EOG signals. Each method has its own advantages and limitations, and the most suitable processing method should be chosen according to the actual situation. Virtual reality technology has been developed for about 40 years, and the traditional virtual reality interaction methods mainly include handles, data gloves, motion capture, etc. In recent years, some studies have started to combine human-computer interaction based on bioelectrical signals including eye electricity, brain electricity, etc. with virtual reality. The combination is usually done by designing a virtual immersive 3D graphical interface and feedback system, in which users can use human bioelectrical signals as a communication medium to interact with the virtual environment in real time. The potential development of this bioelectric signal-based virtual reality interaction technology consists of two main aspects. On the one hand, bioelectricity can be used as a new type of input signal for virtual reality systems, changing the traditional way of interacting with virtual environments. Compared with traditional devices, bioelectric signal-based interaction does not rely on any action or language, and the interaction process is simpler and more direct. On the other hand, virtual reality technology can also be a useful tool to improve the performance of HCI systems, in contrast to traditional HCI systems, where the user interface is usually a simple two-dimensional graphic displayed on a screen. Virtual reality can provide users with more colorful and stimulating stimuli and feedback, which can help improve the performance and ease of use of the system. In addition, virtual reality can also provide a safe and flexible training and testing platform for prototyping applications of various HCI technologies.